The fiberglass industry generates $12 billion annually in North America. The raw material is silica sand melted at 2,500 degrees Fahrenheit, using natural gas spun into fibers, bound with phenol formaldehyde resin that off-gases formaldehyde into your home for years. Now imagine a material that grows at room temperature, in the dark, in a bag, from waste farmers pay to dispose of, zero heat, zero petroleum, zero formaldehyde. Matches thermal performance, exceeds fire resistance, composts in 60 days. One grows in a bag from trash, the other requires a $200 million factory. Guess which one the building industry standardized? The material is called mycelium. It is the root network of fungi. Not the mushroom you see above ground, the vast, thread-like network below it. Every mushroom is connected to a web of microscopic filaments that spread through soil, wood, straw, and any organic matter the fungus uses as food. These filaments, collectively called mycelium, digest organic material by secreting enzymes that break down cellulose, lignin, and other plant compounds. As they grow, they bind everything they touch into a dense, interconnected matrix. In nature, this process holds forest floors together, decomposes fallen trees, and cycles nutrients back into the soil. In a controlled environment, this process can be directed to grow rigid panels of almost any shape, any size, and any density. In 2007, two mechanical engineering students at Rensselaer Polytechnic Institute in Troy, New York, had a realization that should have changed the building industry permanently. Eben Beyer and Gavin McIntyre were walking through a forest when Beyer noticed that mycelium had bound wood chips, leaves, and debris into a solid mass on the forest floor. It was rigid, it was lightweight, and it had formed itself without heat, without pressure, and without any human intervention. The organism had manufactured a composite material from waste, using its own biological processes as the factory. They returned to their lab and began experimenting. They filled molds with agricultural waste, straw, corn stalks, rice husks, the kind of material that farmers in every state pay to haul away or burn. They inoculated the waste with mushroom mycelium. They sealed the molds. They waited. In approximately 14 days, the mycelium had colonized every particle of the substrate. Every straw fiber, every husk fragment, every loose particle was bound together by a dense network of fungal threads. The result was a rigid, lightweight panel with measurable structural properties. They dried it to kill the living mycelium and halt growth, producing a stable, inert building material. They tested it. The thermal conductivity was between 0.04 and 0.07 watts per meter Kelvin. For context, commercial fiberglass insulation has a thermal conductivity of approximately 0.04 watts per meter Kelvin. Published research from multiple institutions, including a 2025 study using mycelium coir composites, has confirmed specific R values of 3.3 to nearly 5.0 per inch for mycelium-based insulation panels. Standard fiberglass batt insulation ranges from 2.9 to 3.8 per inch. The mycelium matches it. In some formulations, it exceeds it. They tested it for fire. A 2018 study published in the journal Materials characterized the thermal degradation and fire properties of mycelium composites. The mycelium panels charred on the surface when exposed to flame but did not sustain combustion. They self-extinguished. The chitin in fungal cell walls, the same structural polymer found in insect exoskeletons and crustacean shells, is naturally flame retardant. A 2022 study published in Scientific Reports grew fungal fibers with a silicon substrate and demonstrated superior fire-resistant behavior, including significantly higher ignition temperatures and reduced flame height. A 2023 article in Scientific American described mycelium as a safer fireproofing material, reporting that researchers at RMIT University grew thin sheets of mycelium that could be used as fire-retardant cladding for buildings. The fungus does not burn the way petroleum-based products burn. It resists flame as a fundamental property of its biology. They founded a company called Innovative Design. They began manufacturing mycelium-based materials commercially. IKEA adopted their mycelium packaging to replace expanded polystyrene foam. Dell used it for shipping cushioning. They won innovation awards. They secured venture funding. Their core technology demonstrated that a living organism could manufacture building materials from agricultural waste at room temperature with zero industrial energy input. And then something did not happen. American home builders did not adopt it for wall insulation. Building supply chains did not shift. Building codes did not update. Fiberglass remained the default. It is still the default today. To understand why, you need to understand what fiberglass insulation actually is and what supply chain it represents. Fiberglass insulation begins as silica sand. The sand is transported to a manufacturing plant where it is melted in a furnace at approximately 2,500 degrees Fahrenheit. Natural gas powers the furnace. The molten glass is forced through fine nozzles called spinnerets, which spin it into extremely thin fibers. These fibers are collected on a conveyor belt and sprayed with a binding resin. typically phenol formaldehyde or modified urea formaldehyde compound. The resin is a petroleum derivative. The bound fibers are cured in an oven, cut to size, and packaged for distribution. The manufacturing process consumes enormous amounts of energy. The raw material supply chain runs through mining operations, natural gas pipelines, and petrochemical refineries. The finished product is distributed through a network of wholesalers, building supply retailers, and contractor supply chains that have been in place for over 80 years. The largest manufacturers, Owens Corning, Johns Manville, Knopf Insulation, CertainTeed, operate factories that cost hundreds of millions of dollars to build and represent billions in invested infrastructure. That infrastructure is the product, not the insulation. The infrastructure, the factories, the supply contracts, the distribution networks, the contractor relationships, the building code specifications that reference fiberglass by name, the material safety data sheets that installers are trained on, the insurance frameworks that underwriters have priced around, all of it is optimized for one material. And all of it represents sunk cost that the industry will defend. Mycelium insulation threatens every link in that chain. It does not require a furnace. It does not consume natural gas. It does not use petroleum-based resins. It does not require a $200 million factory. It does not require a mining operation, a petrochemical refinery, or a continental distribution network. It grows in a bag from straw in a garage in 14 days. You cannot build a supply chain monopoly around a material that anyone can produce from farm waste and mushroom spores. You cannot lock contractors into proprietary purchasing agreements for a product that grows itself. You cannot justify a $200 million factory when the competition is a plastic bag in a dark room. The threat is not technical. The thermal data is comparable. The fire data is favorable. The environmental data is overwhelming. The threat is structural. Mycelium insulation decentralizes manufacturing to a degree that the existing industry cannot absorb without dismantling the infrastructure it has spent 85 years building. Now here is what the health data says about the material that industry chose to protect. Fiberglass insulation is bound with formaldehyde-based resins. Formaldehyde is classified by the International Agency for Research on Cancer as a Group 1 known human carcinogen. Not a possible carcinogen, not a probable carcinogen, a known one. It causes nasopharyngeal cancer in humans. The National Toxicology Program has listed certain glass wool fibers, specifically the inhalable variety, as reasonably anticipated to be human carcinogens. The material that lines the walls of virtually every American home built after 1950 contains a binding agent made from a substance that the world's leading cancer research authorities have classified as carcinogenic to humans. Formaldehyde off-gases from fiberglass insulation for years after installation. The EPA states that indoor air quality in American homes is typically 2 to 5 times more polluted than outdoor air, and building material off-gassing is a documented contributor. Every hour your family spends inside your home, they are breathing air that is passed through or around insulation bound with a known carcinogen. The exposure is low level, it is chronic, and it is continuous. Mycelium insulation contains no formaldehyde, no petroleum resin, no synthetic binding agent of any kind. The binding agent is the mycelium itself. The fungal threads physically interlock with the substrate fibers, creating a mechanical bond that requires no chemical adhesive. The finished material off-gasses nothing because there is nothing in it to off-gas. It is straw and mushroom roots, that is all. For installers, the difference is equally stark. Fiberglass insulation requires protective equipment. Gloves, because the glass fibers cause skin irritation and microlacerations on contact. Long sleeves, for the same reason. A respirator mask, because inhaled glass fibers can cause respiratory irritation and, with chronic exposure, potential long-term lung damage. Safety goggles, because fiber contact with eyes causes irritation. Every professional installer knows the discomfort, the itchings, the coughing, the skin rash that lasts for hours after a day of work. Mycelium panels can be handled with bare hands. They can be cut with a standard saw. They produce no irritating dust. They require no respiratory protection. The material smells like fresh mushrooms during handling. There is no chemical odor, no particulate hazard, no protective equipment required. Now here is where the science becomes even more difficult for the conventional industry to dismiss. In April 2025, researchers at Montana State University published findings on a mycelium-based building composite that demonstrated a property no conventional insulation material possesses: self-healing. The team grew a composite using Neurospora crassa mycelium combined with Sporosarsina pasteurii bacteria that produces calcium carbonate through biomineralization. When the composite was cracked, the living fungal network regrew across the fracture line. The bacteria deposited calcium carbonate mineral bridges in the gap. The crack healed. Structural integrity was restored without human intervention. No fiberglass does this. No spray foam does this. No mineral wool does this. When conventional insulation is damaged, it stays damaged until a contractor is paid to remove and replace it. Mycelium insulation, in its living form, repairs itself. The implications for building longevity, maintenance costs, and disaster resilience are extraordinary. A wall that heals its own cracks after an earthquake. Insulation that regrows after water damage. A building envelope that maintains its performance over decades without maintenance because the material inside it is alive and continuously maintaining itself. And NASA has taken notice. In 2018, NASA Ames Research Center launched the Myco-Architecture Project under the NASA Innovative Advanced Concepts Program. The project has received over $2 million in funding across 3 phases. The premise is straightforward. When humans build habitats on the Moon or Mars, they cannot ship conventional building materials across millions of miles of space. Every pound costs approximately $10,000 to launch into orbit. Shipping enough fiberglass insulation for a single habitat module would cost more than many nations spend on their entire space programs. The solution NASA is developing is to ship dormant fungal spores, activate them at the destination using whatever organic substrate is available, and grow the habitat structure in place. Walls, insulation, structural panels, all grown from mycelium, at room temperature, in the dark, without a factory. The same agency that put humans on the Moon in 1969 is now planning to build the next generation of space habitats from mushroom roots. The material is considered reliable enough for NASA to invest multiple millions and multiple years of research for the most hostile environment humans will ever inhabit. And back on Earth, where agricultural waste is free, where mushroom spores cost $12 online, and where every home in America needs insulation, the building industry continues to fill your walls with petroleum spun glass fibers bound with a known human carcinogen. NASA is growing buildings for Mars. Your contractor is selling you fiberglass from 1938. For anyone who wants to experiment with this material, the process is accessible. You need a substrate: straw, wood chips, sawdust, corn stalks, or any agricultural waste. You need mushroom spawn. Oyster mushroom spawn is widely available online for $10 to $15 per bag, enough for multiple panels. You pasteurize the substrate by soaking it in hot water at 160 to 180 degrees for 1 to 2 hours to kill competing organisms. You mix the spawn into the substrate, pack it into molds of whatever shape and size you need, seal the molds in plastic bags with small air holes, and place them in a dark space at room temperature. Within 3 to 5 days, you will see white mycelium threads colonizing the substrate. By day 10 to 14, the entire mass will be bound into a solid white block. You remove it from the mold and dry it thoroughly, either in the sun or in an oven at low temperature. Drying kills the mycelium, halting growth and producing a stable, inert panel. The dried panel is rigid, lightweight, and can be cut with standard tools. Its thermal performance is comparable to fiberglass. Its fire resistance exceeds untreated fiberglass. It contains no toxic chemicals. And when the building is eventually demolished or renovated, the panel can be composted. In 30 to 60 days, it returns to soil. Compare that to fiberglass, which will sit in a landfill for over 500 years without decomposing. The EPA estimates that over 600 million tons of construction and demolition waste is generated in the United States annually. A significant portion of that is insulation that will never biodegrade. The economics at the DIY level are remarkable. A homesteader growing mycelium panels from free agricultural waste and $12 in mushroom spawn can insulate a small structure for under $20 in total materials. The equivalent fiberglass insulation would cost $100 to $200 at a building supply store and would require gloves, a mask, and long sleeves to install. The mycelium panels are installed barehanded. At industrial scale, Ecovative Design has demonstrated that mycelium composites can be produced at costs competitive with conventional materials when agricultural waste feedstock is sourced locally. The company's manufacturing process uses 98% less energy than expanded polystyrene foam production and 90% less energy than fiberglass manufacturing. The carbon footprint is a fraction of any petroleum-based insulation because the material is grown from agricultural carbon rather than extracted from fossil reserves. The technology is not waiting for a breakthrough. The breakthrough happened in 2007, 18 years ago. It has been refined, tested, published, commercialized, adopted by multinational corporations for packaging, funded by NASA for space habitation, and validated by multiple university research programs across 3 continents. The only place it has not been adopted is inside the walls of American homes. The one application where it would affect the most people, save the most energy, eliminate the most toxic exposure, and divert the most waste from landfills. And the reason is not that it does not work. Every published test says it works. The reason is that the $12 billion fiberglass industry has 85 years of infrastructure, supply chain dominance, building code integration, and contractor relationships that a mushroom growing in a bag cannot compete with on a purchasing spreadsheet. even when the mushroom wins on thermal performance, even when it wins on fire resistance, even when it wins on health safety, even when it wins on environmental impact, even when it wins on cost at the DIY level. The spreadsheet is not designed to measure what the mushroom wins on. It is designed to measure what the existing supply chain is optimized to sell. That is the answer to the question this video started with. The building industry did not standardize fiberglass because it was the best insulation material available. It standardized fiberglass because it was the best insulation material for a centralized, petroleum-dependent, factory-scaled manufacturing and distribution model. Mycelium is better for the homeowner, better for the installer, better for the planet, better for the landfill, and better for the child sleeping behind the wall, but it is worse for the supply chain. And the supply chain decides what goes in your walls. The science is published, the material is proven, the mushroom spawn is available online. The substrate is in every farm field and every yard waste bin in the country. The growth time is 14 days. The cost is negligible. NASA trusts it for Mars. Your walls are still filled with the product from 1938. Now you know why. And now you can grow the alternative in your garage.